This is a quick introduction to center of mass in one dimension. And the way you can think about center of mass is that it's a weighted average of the positions of all the masses. And what I mean is that where you have a larger mass, the center of mass should be closer to that. Where you have smaller masses, the center of mass should be farther away from that. So I'm going to write down that the center of mass position is given by taking each x-coordinate and weighting it according to how much mass is there, and then dividing by the total mass, which I could write as the sum of all the masses in my picture. So this is actually exactly how you find a weighted percentage of a bunch of test scores, for example. I would take the importance of each test score, like what percentage of your final grade it counts as, and multiply by the percentage you got, and do that for all your exams, and then divide by the total number of points. So it's the same basic idea. This could be written in summation notation as the sum of all the mi's times xi's over the sum of all the mi's, or more commonly as 1 over the total mass times the sum of all the x-coordinates multiplied by the masses sitting at those x-coordinates. And it turns out the center of mass just pops up in the theory of mechanics frequently. You'll end up being able to simplify an expression by finding this piece. But it also takes on a life of its own. It has a lot of interesting properties. So for example, the center of mass of a system is also the balancing point of the system. Another interesting example is if I painted a spot of white paint on a wrench right at the center of mass of that wrench, and then I chucked it into the air, I would see that white spot traveling on a perfectly parabolic trajectory, just like a point mass in projectile motion. Okay, let's get a little bit of practice applying the formula to a one-dimensional distribution of mass. In this example, I've placed a 1 kilogram mass at the origin, and I've placed a 2 kilogram mass at 50 centimeters to the right of the origin. Now, intuitively, if you think of a center of mass as the balancing point of a system, I can imagine that these are connected by a light rod that has negligible mass. And I try to think to myself, where would I put my finger in order to balance the system? And it should be closer to where you have more of the mass, and that's exactly what this weighted average formula accomplishes. So let's actually compute the thing. X center of mass should be 1 over all the mass put together, which is 3 kilograms, times the sum of each x coordinate multiplied by the mass that's at that coordinate. So I have 1 kilogram at x equals 0. It's perfectly fine to work in non-standard units here. I'll just get centimeters for my answer. And I have 2 kilograms at 50 centimeters. I grind through the math, and I get 33.3 centimeters for the balancing point. Definitely closer to the heavier mass.